Hello, and thank you for joining us for our Automotive Bluetooth Audio Test webinar. My name is Eric Hodges. I'm the Director of Marketing and Sales Operations for Audio Precision, and I'm very glad that you can join us today. Without further ado, I'm going to turn it over to Mike Martin, our Product Manager here at Audio Precision. So take it away, Mike.
Thanks a lot, Eric. Greetings, folks. It's a pleasure to be with you this day, whichever part of it you're in. And as planned, we'll be talking about automotive Bluetooth audio test here. A little bit about me. My background is electrical engineering, though I've spent the vast majority of it focused on test and measurement and less on actual design work. Great chunk of my career was spent as a test engineer, and so test is near and dear to my heart, and this particular technology is interesting. It's used in a lot of different applications, and we'll be focusing here today on automotive Bluetooth. So with that, let's go ahead and get started. As soon as I redirect my screen. So our agenda today is shown here. We'll do a brief intro to Bluetooth, talk a little bit about audio quality in Bluetooth channels, profiles, and roles. We'll step a little deeper into the discussion about profiles, then move on to a little bit about the APx analyzer and the Bluetooth option for that. And finally, we'll move on to what's necessary to set up a measurement, going through the discovery, pairing, and connection process, and then steps in connecting the analyzer to the device and making measurements. So in today's session, we'll be using this single DIN head unit that you see here. It's been around a little while. It's not a brand new design, but it actually will work fine for our discussion here. It's very compact and relatively straightforward to work with. So the measurements that we'll be making will be made on this particular device. So maybe the first thing I should say to you about Bluetooth for automotive is it's really not different than other Bluetooth devices as far as the testing part of it goes. Certainly there are elements that are unique to the automotive side of it, but here we see, you know, a head unit with it preparing to do a connection to either a phone, which is a bidirectional path, or in this example, an audio streaming device, maybe MP3 or MP4, that's sending audio data into the system. And those are, in fact, the primary elements that are in the Bluetooth connection for cars. So, so we'll be kind of focused in these areas. And with that is the recognition that there's kind of two levels of audio quality associated with Bluetooth in cars. One of them is the hands-free phone connection, which has a bandwidth of about 3.6 kilohertz. It is a two-way communication, but it doesn't have a great deal of fidelity in that narrow band. It does the job, it works well, people use it every day, so there's not a lot to complain about, but it is quite different than the advanced audio distribution profile, also called A2DP, which provides near CD quality bandwidth of a full 20 kilohertz. That is the one-way communication channel streaming audio data into the system. So we'll talk about Bluetooth profiles. What that is, if you're not already familiar with it, is a set of functions that two devices use to communicate with each other. And so there are a number of different profiles. I'll talk about them on the next slide, but just remember it's the defined method, and both devices that are going to communicate need to speak in that same language, if you will, using those same functions. Also, you know, when it comes to roles, Bluetooth devices are either a source or sink. And in the automotive world, when it's discussed, it's typically discussed relative to the head unit. So the head unit is in source mode or sink mode. So let's move on then and just talk a little bit more about profiles. There are a lot of defined profiles for Bluetooth, but in fact, only 3 of them are really relevant to what goes on in cars. And I've mentioned the A2DP high fidelity channel profile. Um, there's also an audiovisual remote control profile that is relevant. It's what allows you to use the button on your device to skip forward or backwards. And it's available through the Bluetooth connection. And down here at the bottom is hands-free link. So these are the 3 primary elements. What I've shown here in the box with the blue header is the pull-down list of what's available in the Bluetooth selection set for profiles in our analyzer. And this top one is shown as a source for A2DP and then hands-free phone audio gateway and remote control target. So this hands-free phone is the source side of this selection we would like, and likewise down below we have the sync side also with hands-free phone. So these 2 are relevant to automotive testing. These other 2 are related to headset tests particularly, though what goes on is quite similar to what we talked about for automotive. Okay, here at the bottom of this picture are a couple of our modular analyzers, and you can see that in each of these there's a module with a couple black antennas on it. This is what we call the Bluetooth Duo module, and here is a close-up of that module, and it has a source side, and now this is referencing the analyzer, and a sync side. And so it has actually 2 radios, and it's available as an option in any one of our modular chassis. So here is our classic APx 500 modular chassis. We have a quite new instrument that was brought out at the end of last year that is also modular. It has 1 module slot down here. This is an electroacoustic test system. It has power amplifier and microphone inputs and a lot of other useful stuff for electroacoustic testing. But Bluetooth is available for either of these types of analyzers. So,
Mike, a question is, what's obviously it's integrated into the analyzer. What's specifically the advantage there as far as using a third party or standalone Bluetooth adapter?
Yeah, that's a really good question, and it's I'll talk more about this as we go because it'll become apparent as we start working with the actual analyzer. But the level of integration of this module is amazing, actually, from my perspective. Things that need to be done with the module can be done in a number of different ways so that you can get to the control in the shortest amount of time. And this device, whether it's acting as an input or an output, it acts and behaves like any other of the modules that we produce, which means it's just another source or sync, another part of the system, and there's nothing that feels poorly thought through or not really purpose planned like this module is. So we'll be talking about that along the way. I'll highlight a couple of cases where I think the implementation is quite smooth. All right, so as you move towards starting to get ready to make measurements, maybe the first thing to say is that you should know about the DUT, the device under test that you plan to test. Everyone has its own personality and control process. This particular unit, one of the things I needed to know about it is that it has a pair of front speakers and a pair of back speaker outputs, and the hands-free phone support is only available on the front speakers. So that makes sense, assuming that the driver might be the one speaking and you'd want the speakers for the driver to hear up closest to the driver. And so that was one element that was important. If I had picked the wrong set of outputs, I wouldn't have ever been able to measure the hands-free phone output signal. The other one is that this volume level that's controllable through the knob on the front panel of the DUT is automatically reduced to minimum at power up. And so it's necessary to set that level, and we'll be talking more about that in a minute or two. And then the other thing is to know what profiles your DUT supports. I'm going to spend a little more time talking about profiles to drive home the point of why this matters. Some profiles have higher quality signal or perhaps less latency through them, and that impacts your measurements. So so this is an interesting thing to have some knowledge of. All right, so now we're moving closer to actually starting to think about the measurements, and what we do is specify connections in something we call the signal path setup on the analyzer. I'm going to talk about that in just a moment or two, because this really begins to drive home the fact that this isn't just a piece of hardware that was plugged in that perhaps was a third-party device or something like this. This is a highly integrated part of the system. All right. You likely know from working with your Bluetooth speakers at home, or perhaps you've already done a lot of this testing. There are really 3 steps that need to be done in order to connect up to a device before you can make any sort of measurements. And so the connection process is basically a discovery process where the analyzer scans the area and lists any Bluetooth devices that are not hidden, undiscoverable. And it may well be when we take that step here in the demonstration that you'll see other devices besides this particular unit that I'm planning to do some testing on. Once you've gone through the discovery step, the next step is pairing, and it's pretty straightforward. You hit a button and the 2 devices kind of handshake across with each other and complete that process. And once they're paired, then you make a connection to the device and you're ready to do some testing. So these are key steps, and it's really easy to forget or miss part of it, or get halfway through a process and want to stop at a point and restart it at that point, and you might find that you need to redo this process in order to get back to a known state. All right, so here's some status indicators. You'll see these on the actual analyzer display in a couple of minutes, but I'll talk through the fact that there is a status indicator for both output, shown here, and input, which I'll show you on the next page. And this gives quick at a glance information about the state of the Bluetooth connection. In fact, or any other kind of connection. We could potentially have a PDM output or something if we're testing different devices. But in this case, we would see that the output was set to Bluetooth. It would have a device descriptor. It would tell us what mode we're in, whether we're in A2DP or HFP. And if we're in HFP, then we have this SCO, and it is either in a state of not connected or connected. And if you see the big red bar on the screen, you won't be able to do any testing until the device is actually connected and going. So we'll talk about opening SCOs as we go along here. And this second line shows what it looks like when everything is copacetic, when it's all working like it should. And so it tells us the same information we saw up here. It tells us which codec is being used and the sample rate. So SCO, which I mentioned up above, is synchronous connection oriented link. And it's a process used for voice data transmission. CSV is a continuously variable slope delta modulation codec There are lots of codecs for different purposes. This is one example that's used in Bluetooth, maybe the most common for hands-free phone work and headset work. And finally, there are codecs, and codecs are the process to reduce the streaming data down into a form of information that the A to D converters and D to A converters can handle to make real values that can turn into a waveform. So codecs are the process in between the radio and the ADC or DAC to convert the data into the necessary form.
Hey, Mike, in regard to the SCO,
Yeah.
if you're testing a Bluetooth device that was not a phone,
Yes.
did not require HFP, HSP profiles, but was just A2DP for streaming music, is a SCO connection still going to be required if you're testing that?
It is not relevant in that
Okay.
case. Good question. Yeah, it's only related to hands-free phone connections in this case. And so this is, and it's worth mentioning that a really easy mistake to make is to not make the connection with the SCO, not open the SCO, and then try to go on and do a test, and things won't work right, and you won't be able to understand until you glance back at the status indicator or other measures to determine that that's the problem. All right. Here is an example of the full monitor status indicator bar, and it's showing that we have an output is an analog unbalanced 2-channel connection, and input as Bluetooth with a new device that we haven't talked about, just a different device. In this case, we're doing streaming audio, and it's a A2DP connection for the profile. The codec is SBC, and the sample rate is 44.1 kilohertz. So this is what you expect to see, is a lot of nice green information across here. If something's red, there's a need to stop and look at it. And it's probably worth mentioning that SBC is a Bluetooth special interest group. It's referred to as the Bluetooth SIG. That is the standards body for Bluetooth, and they've specified that SBC codecs must be included in any A2DP connection. It's possible to use other codecs that might have better performance, but this is a single codec that must be in the system for any device to use that might want to do streaming audio. All right, so with that, I think we'll move on to hopefully some more interesting stuff than just looking at slides. And what I'll do is just briefly drop this out of the way. And what you see in front of you now is the user interface for the Audio Precision APx 500 analyzers. This software is compatible with a broad range of analyzers, starting down at relatively low price and performance range, and going all the way up through our APx 555 industry-leading performance unit. So that once you're familiar with this user interface, it becomes easy to use any one of the analyzers. I'm going to take a few minutes or a couple minutes to just introduce, for anybody who maybe hasn't used this software before, what the layout is, so that you get some better comfortable feeling about what's here. Over on the far left side, there's a box called the Sequence Navigator, and this area allows you to pick and choose tests that we provide in the software and place them in any sequence you prefer, and then to string them together so they'll all run sequentially, all without writing any programs. So automation is kind of built in this from the beginning. Now, it is possible that you can drive the analyzer from an outside piece of software like LabVIEW, but with the amount of automation built into the sequencing here, it's often not necessary. And what you end up doing is producing project files that you can simply recall and run and perform the test. So this is a bit about the sequence. We'll be using it in a few minutes. In the center here, or somewhat center, is the signal path and measurement setup area. So in this area, I define what I'm going to use for an output device and what I'm going to use for an input device. And then I've got down here a little panel that allows me to verify connections. So this is used for getting the definition defined for what channels will be used and what kind of channels they will be. So for example, I have a lot of choices here, and there are a number of other things in my system. For example, a PDM module that I could use for this if I was testing, for example, digital microphones. So this panel toggles with this arrow up here, and if I select a particular test, then it becomes the control panel for that test. And so here you can see I've selected frequency response, and I've defined or predefined in this case, what the frequency range should be and what the level should be, and I can go in and change any of these that I choose to. And once I'm done with the setting and I have valid connections, I can run the test, and that running of the test, the whole sequence is simply pushing this button right here. An individual test can be run hitting this button, but it doesn't execute the whole sequence. And then finally, this area is obviously the data display. And depending on the test you run, you may get 1, 4, 10, 12 different types of measurements as outputs from the tests that you perform. So excuse me for a moment. I'll drink water. So we will, in a moment, actually manually configure a test and run it, but I thought it'd be good to at least talk about the layout. There's one other element down here, which is a monitors and meters area. And we have a scope display, which gives you a nice time domain view of what's going on with the signals that are acquired, a spectral view through an FFT panel. And again, kind of circling back on that comment I made earlier about integration, there actually is a Bluetooth monitor. And if we pop this up so we can get a closer look at it, you can see that there's a number of different things. Now, at the moment, this is not active because I haven't chosen any Bluetooth channels. But as soon as I do that, then it's active. And there's another really great bit of integration here that's a very commonly used panel. I'll call it back in a minute so that I can finish talking about this. So there are actions that we can do here. Depending on other things, we can do remote control and attention command logging, and then review those if we're looking for some kind of hiccup in processes that should have gone on in the system. So not only do we have waveform monitors, but we have Bluetooth monitors as part of the integration. All right, so let's go ahead and, I'll mention one more thing. This is what I consider the primary user interface, but for some people, they prefer the bench mode to sequence mode, and I'll just pop over to that. It takes a second or two to switch, and you'll see the color's a little different. It's kind of a green tint, and it doesn't have sequencing. This is designed as an interactive tool. The meters actually have higher update rates on them in most cases. So you can do a lot of what you would do in a sequence, but you do those as manual steps. The control for setup looks quite the same. So we could select a Bluetooth output or input here. And we can turn the generator off and on, which is something like that control I showed you previously, and control how the signal is being analyzed. It's a useful tool, and it's very good if you're trying to, for example, monitor a certain output over time. You have a time recording capability. So this is a really great interactive R&D kind of tool if you're just trying to pound on manual tests that you want to do. But to do complicated tests that you might need or want to repeat lots of times, the sequence mode is really a great thing. All right, so let's actually set this device up to test. And right now the DUT is setting with the source selected to Bluetooth audio. I'll just scan through one more time so it knows it should receive a Bluetooth audio source. And then in order to pair the device, I need to put that into pairing mode, and I hold the Bluetooth button down for about 7 seconds, and then there'll be a little Bluetooth logo flashing on the screen. And once I have that, I can click on that little gear up here in the corner, which brings up a setup panel for Bluetooth. And so what we'll start with is so I should mention that when we select one of these lines, we're actually enabling all three of these profiles. So you'll see that over here, all of these are checked at the same time. That's okay. The analyzer can be told what mode it's going to be in during the test process, and it'll automatically resort to the proper profile. So next we'll scan for devices. And this Bluetooth speaker is probably mine here in the room. I don't know whose phone this is. Somebody's near enough by that I can see it. I'm not going to try to pair to that. And my device that has now, as soon as I pair, will officially be paired. And it's looking for, if it needs it, a PIN number to be entered in as a security device. There is a mode which you can see up here called Secure Simple that allows you to not have to set a PIN. If the device you're working with requires a PIN, I'll try to do this before it gets out of that mode. Then you have the option of setting it up so that you will use a keyboard or display in buttons to enter in the PIN number. So everything's covered, but this just works mode is especially convenient. So now what we see is that I've scanned for the devices, I've paired, but remember this is a 3-step process, and down here at the bottom of the screen, you can see that the status indicator is telling me that I've not connected yet. So I still have that last step, the 3rd step, to connect, and I'll specify that I'm going to do A2DP. All right. And so at this point, we have the system connected, and it's able to send an output stream into the device under test. And then we need to set up channels to receive the speaker output from the head unit. And this is fairly straightforward. I've already got the connectors connected to the analog unbalanced signals. We're not doing an acoustic test. We do make acoustic devices, test system models that would be useful for doing that. But in this case, we're just collecting electrical signals. So all of that is already in a good state. And so that's really what we need to do about test signal path setup. What I like to do at this point is take a look at one of these monitors and turn on the generator, because if I've got everything set up right, I should see a 1 kilohertz tone or any other frequency or amplitude that I wanted to based on settings here. But this gives me some confidence that it's going to work that the connections that I made up here are correct, that the digital signal coming out of the Bluetooth is being received by the head unit and being translated into analog signal that comes to the speaker outputs. Okay, so the next step that we need to do is set the level, and you know, you would like the signal generally to be as large as possible, just to get well away from the noise floor of the system. And for digital devices like this Bluetooth interface, we don't generally set to 0 dB full scale, which is the maximum output. So often we would go to -3 dB. Oops, it didn't like the dB. I think I can just say -3. And now the amplitude has increased. We see a couple small harmonic spurs out here. So we've got this in a reasonably high output place, but we would like to know, could we get more out of it without degrading the signal? And so it's kind of convenient just to toggle the amplitude up, and just going from -3 to -2 dB, you can see a lot more harmonic distortion here. So this is a great step to do, and also notice that if I go the other way, those few spurs that you see, harmonics that you see there in the spectrum, don't especially reduce if I lower the amplitude. So that -3 dB full scale is certainly a sweet spot for this. And it might be illuminating to you to just see what that looks like as a time domain waveform. Clicking it up one notch, you can actually see the flattening of the sine wave. So that is a bit about getting the device receiving the Bluetooth to have maximum signal input. Now, I mentioned that the DUT has a volume knob on it, and I can adjust that to anything I would like. Again, being well out of the noise floor gives you a better signal to noise ratio. So what I would like to do, and I think I'll go back to the spectral view in doing this, is just adjust the output until it's at a high state but not causing distortion. And there's the distorted spot. All I'm doing is turning the knob here on the front of the DUT, the front panel. So this looks like a good place as well. So now I've got a 200 millivolt signal coming out of the device under test, and we're ready to make a test at this point, which is pretty exciting. So what we'll do is select a new test, because these tests are okay, but I kind of like to run a continuous sweep, a chirp frequency sweep on this. So I select our add a measurement menu, and this shows you all of the measurements that are available. You can also, if that's a little overwhelming, you can kind of pick categories that are related and look for the thing you want there. I can see that my continuous sweep is here, so I'll add that and close it. And now we've got a measurement setup in front of us. So we talked about the fact that we'd like to test this at -3 dB. So I've made that setting here, and we've now got the right connection, and we've got a test we'd like to run. Let's go ahead and run it and see what happens. Now I could click on this button and run the sequence first, but I'm going to just do a quick test by hitting this start button, and it will run only that one scan. It produced a lot of results. You can see the frequency response plot here, and then thumbnails for a lot of other results that come out of this test. And this isn't anything at all that we would expect to see. We would expect to see a roll off down here, low frequency, come up somewhere around 100 or 200 hertz, stay really flat until just before 20 kilohertz and drop off. So something has gone desperately wrong here, and now we need to figure out what that is. So what I'm about to show you is maybe the best tip or trick I learned about troubleshooting things in the system here. So in amongst all of these results is an acquired waveform display, a time domain waveform display. And there are two things that really jump out at me here. The first one is this oddity, right here in the sine wave. Normally we would expect a very slow startup that would be completely continuous and be continuous right up to the point it ended the sweep, and then you would see a decay down to a very quick decay down to zero signal basically. So this is unusual, and the fact that we don't see this decay out here is unusual. And the ringing that we saw in the frequency response here, this ringing, we were actually looking more at this, is due to not capturing, having an abrupt cutoff of the signal out there at the end. So let's try to figure that out first. And one of the things that's helpful in doing that is to add another measurement. It will give us a little bit more information. And what I have in here is a DUT delay measurement. Delay is something that you have to be ready to work with in Bluetooth, because every Bluetooth delay or Bluetooth device has its own delay time. It depends entirely about how the design was created and what the designer did. And in order to get a good acquisition, you're going to have some understanding of what the delay is. So what I'm going to do here is just run that delay all by itself. And it tells us that we have 144 or roughly 145 milliseconds lag time between the time the signal hits the system from the Bluetooth Duo unit until the time that the signal starts swinging on the output. And there are a couple of ways of handling that. One of them is that in the signal path setup, we could actually go down and enter in a DUT delay of 145. And I think once we do that, whoops, I forgot milliseconds. And once we do that, we can come back to our continuous sweep test and start that again and see if the results are any different. And there you go. Now we still got some irregular behavior out here, but it looks a lot more like we expected, and this part looks completely reasonable. So what we've done for that DUT delay is okay if we're only going to be testing this DUT in this mode, but it could be that if we later on in testing selected a different codec, or we went from A2DP to HFP for hands-free testing, that the delays would change, and then we would be back to having problems. So rather than having a single delay that we hope works for all of them, we'll take that out. And what we'll do is go back to the measurement setting for continuous sweep, and we will adjust the time settings here. So the pre-sweep is something I'll talk about in a moment, but if I extend this acquisition to something on the order of about maybe, I don't know, 340 milliseconds might be a good number, then things will start behaving. I also know that this particular continuous sweep is actually quite efficient, and I don't really need to take quite this long running it. So I could reduce this down to something like 150 milliseconds. And this will, I think, still allow the sweep to go out to the 20 kilohertz range, perhaps a little bit unusually, but it's there. So let's look at what's still happening on our waveform. you can see now that and this is stereo channels that I'm testing here. So you see a blue trace and a red trace. They are phase offset on purpose. That's a technique we use in crosstalk testing to make the crosstalk test more efficient. But you can see we still have this issue here, and until we sort that out, we're going to have an odd response on the system. So what we need to do is add some pre-sweep time to allow the system to more gradually ramp up in frequency before it starts trying to swing the device. So these will affect things, and at this point, it doesn't really have a significant impact on the shape of the response. But I'm going to turn off the crosstalk phase change and just run the test again, and I think you'll see that things look quite different now. So those two traces are still there. Channel 1 and channel 2 are both still active, and they're right on top of each other. And now if we go and look at the response, we have a very clean response that goes all the way out to 20 kilohertz and drops off. So this is, I hope, a very useful little walkthrough, because taking a look at that time domain signal can give you a lot of information about what's going on with the measurement. Here is the same data, but in a relative form. So it's referenced to 0 dB at 1 kilohertz. So so I think that's a good bit to consume here about the test. But I think what I'd like to do now is talk a little bit more about sequences. And all of the process about signal path and setting up for the tests inside sequences still is the same from what we've talked about so far. I think what I'll do is start by loading a project that I already have. And in fact, I want to go to Open Project. And here I've got a number of projects. I'll grab this top one here. And I don't need to save that nice test we just created. I'll set that aside. And takes a second to load this. And I will minimize the tests themselves and just show you how this sequence was structured, and begin to give you just a small feeling for how efficient and well laid out this is, and also how much work can get done inside these sequences. So the basic sequence that's here is one that tests the A2DP connection. It then goes on to check the hands-free phone sync connection, and in this case we're talking about the sync relative to the device under test. So this is inputting a Bluetooth signal and receiving the audio signal, and finally an hands-free phone source, where the device under test is the source, and we'll receive Bluetooth data from the test. Okay, so before we try to run these tests, I think what I would like to do is talk a little bit about a couple things. First off, one of the things that's a standard part of the software is the ability to produce reports on the measurement results. And this allows you to turn that off or on. When you're doing real testing, it's a really convenient thing to produce a document. It'll create a PDF that you can save away, or other formats of document. But while we're doing interactive things, it tends to pop up each time we run, and it's just something you have to set aside. So I'm going to leave that off for now. I'll try to remember to turn it back on the last run we do here. Inside each one of these are many steps. And in fact, for each one of these items you see here, you can see that there are also little arrows that I can click on that show you the sub-steps of this step. So this is where I specify, for this case, a stepped frequency sweep, and what kind of results I want to get out of it. I'll just mention that it's great to get these results if you can use them. If a particular type of result isn't interesting to you, turning it off will mean that you don't see that data here, but it actually means that you can speed the testing up just a little bit because the system doesn't have to calculate the values that populate that particular result. So it's a nice little thing to keep in mind. We won't be quite that critical here today, and I'll just go ahead and leave all those checks. But you can see here that there are a number of things we can do. We have some basic measurements that produce mostly bar graph type measured values. You saw one of those in the DUT delay. And so these are interesting and available to you as defaults, and then all those other tests that we talked about are available to add through that add measurement button that I used to get the DUT delay measurement out of. So you can recreate this, add new tests, take away tests, select pieces that you don't want as outputs. It's completely flexible, and it's just through this user interface. So I have a step frequency test, and this one says A2DP. What I would like to show you is what's going on in these steps that are down below. So you have the ability to add in additional steps, and bringing myself back to the topic of integration, these steps include control of the Bluetooth channel. So you can do the basic things like connect and disconnect and set transmit power and stuff like that. But you can also, for example, open and close a SCO on a hands-free link. You can dial and ring the device under test. For ADP, you can start streaming and stop streaming. And for remote control, you can adjust the volume. So these are yet another indication of how well connected the Bluetooth option is into the system.
Hey, Mike, we have what looks like a kind of a two-part question,
Okay.
kind of combining the sequence mode discussion and delay. And it's since delay is as you flagged an issue potentially with Bluetooth test, can that delay measurement be built into a sequence, and can the sequence then automatically apply that delay that's measured to the rest of the sequence?
Yes, the answer is yes. And in fact, when I demonstrated that delay measurement, I added it into this sequence right here, and I can tell it to. In fact, one of the ways of handling this would be to go ahead and use that DUT delay value in the signal setup path, the signal path setup, and then change it to another value later if I get to a mode where it's using a different value. So that is an entirely practical way to handle that. It can simply be switched on the fly through the sequence process. All right. Was there a second part to that question, or is that it?
The two parts were doing the DUT delay in a sequence, and then the second part is can the results of that step or measurement be then applied to the rest of whatever you're doing? Yes. So that was the two parts.
Yes. Okay. So so this is a fairly sophisticated capability, and I can add Bluetooth stuff along the way that will control the particular and I'm not getting what I want to see here. It must be getting late in the day. So here's an example. Here we're going from the A2DP setup that we used initially to hands-free sync mode. And here are steps that are directing the device under test to change modes so that we can continue on with a hands-free test. And likewise, when we're all done, we can actually we can turn off the SCO, and we can hang up the connection since we're using hands-free, and then it'll be ready to go in the next test for the A2DP mode that we would want to test. So here's the A2DP startup. So you see a command to start streaming, and here is in fact the measure and set DUT delay. So if I click that, it would automatically set it. At this point, I think I've dialed it in as a fixed value in the project, which is a perfectly fine way to do things. If, for example, you're on a test bench and you're testing the same type of device over and over again, you know, each one of those will vary a little bit from measurement to measurement and device to device, but it will generally be in some close ballpark. Whereas if you were in a condition where you were doing a lot of completely different kinds of DUTs in a day or something, you might just want to set it up as measure this particular device and then make the setting. All right, so we've got a little bit of time here. I will go ahead and run this, and then we can look at some of the output from this test. And I can either leave these all expanded, and just as a reminder, the items that are checked are those items that gets executed, and the items where the boxes are not checked are just skipped over. And so I'm in this first portion of this, the A2DP section, I'm going to do two sweeps, one a step frequency sweep, which is a relatively slow thing to do, but is kind of, I think, still today considered the gold standard for sweeping. And then I'll follow that with a continuous sweep, and we can just kind of compare them quickly as we go. And then we will move on to hands-free phone testing. We'll make these changes that are described here. And here you can see that, in fact, I do have the DUT delay set to change, because what I can tell you is that there is quite a different delay between hands-free mode and streaming audio mode on this DUT. And again, I've got, I won't need that DUT delay test in here, but I've got another continuous sweep element here before we move on into hands-free source. And here, those items that I showed you previously, again, I'm changing, I have the potential to change the DUT delay. I'll talk maybe once more about that when we're, I'll mention it now. One of the things that's interesting is hands-free sending a Bluetooth signal into the device is not so different than what we saw in the streaming audio connection, but when we're sending the signal in electrically through the mic input to represent the phone input, hands-free phone input, if somebody had a mic in their car cabin, then the signal propagation into the device is very quick, and there's some amount of time coming back out of the radio, but it's actually relatively short compared to the others. Okay, so and in each case, I've just chosen to do a frequency response because we can. I will say ahead of time that these aren't all picture perfect responses, and if I knew some more things about the design, it might make a little more sense to me. We can maybe glance at those here. We've got a few minutes remaining. So I've started the sequence, and it's asking me which device I'm going to test, and there's my device under test, Explode, XPLOD. So I'll select that one, and all profiles is still a perfectly good setting, and so I can click OK. And now it's getting into the A2DP test already, and we can actually watch it sequence through here if I can keep up with the system. So now it's doing the step frequency sweep, and again, this takes a little while, but it produces a predictable output, and much like you would expect. So I've got this set up for a 61-point sweep. It's 6-octave ISO R series, and just about done with it here. All right, so we've done that test. It's produced a number of different results, and now it's moving on to do the continuous sweep. And we're done with that. Actually, not that one. That was old data. It's going to make that was actually the response that we saw. And what we just flashed through was a transfer function test. And now we've switched over to hands-free phone. And this is the result we saw for our frequency response there. And now we're switching over to source. This is maybe the most interesting of the response plots that comes out of this process. Okay, so we've now completed that block of testing, relatively efficient. It would have been a lot faster if we had left out that step sweep, but I think it's a good base point. If I was doing real testing, I would say, okay, I'm satisfied that the continuous chirp sweep is a fine way of producing the same results. So we can again kind of quickly run through these outputs. Gain, there's deviation across the band, which is all on the lower end for this particular case. Phase measurement, and there are some things that we can do with this as far as how we want to look at it, whether it's linear or logarithmic, and whether we want to auto scale or fixed scale. So you can see the phase is very, very flat through this channel. You would expect that. We've got a THD plus N ratio value showing here, and you can see through what would be considered probably the most of the usable spectrum. We're down here in the 0.1% THD, which is a good reasonable target to look at. So again, a number of other things, and what gets produced out here depends on the tests that you choose and whether you want to see these results or not. Here's SYNAD, which maybe most people don't look at. So these are things you can pick and choose from, and if you don't need it, then I encourage you to take it out. It'll make your testing run just a little bit quicker. All right, so there is that test. Here's our continuous sweep data set for streaming audio, A2DP, and you can see it looks quite similar to the step sweep. Really the same data. There's our phase here. I'll probably want to do this and auto scale. And so I can present this in a number of different ways, but I think this perfectly shows the linearity of the phase across the spectrum. If you're into group delay, we can give you that. So lots and lots of results. Let's move on here. We've now moved down into the hands-free phone sync test, and we have a continuous sweep for that one. And this is certainly a different looking plot, and one of the things that jumps out is it only goes up to 3.63 kilohertz, and that's the bandwidth you have. So You know, I don't know that all designs would show this kind of response. If some might show something else, but this is what we saw with this particular device for this test. So it's I think a reasonable display. Moving further down here, we now come to the test where we're having the microphone data come out to the Bluetooth unit. And what I see up here is a very well controlled bit of frequency response. And I guess what I see from this is that the expectation is the microphone is not going to have a lot of very low frequency content, and it's going to do everything it can to cleanly acquire in a range from 700 hertz to 3.6 kilohertz, and that gets passed through. So I was kind of surprised at that result, but I did it a number of times and played with a number of things to see if I could make any variation. And of course, getting back to where we started, one of the first things I did was inspect this time domain signal, and lo and behold, you can see exactly the shape that we saw in the frequency response just in this particular waveform plot. So I think that brings us to a good state. We've run a minute or two past. I don't know if it's worth running the whole thing one more time. I think what I could do is turn off the step response up here, so we don't have to run that, and then very quickly just make sure I check all. And then maybe we can very quickly produce an output report just so you can see what that looks like.
And Mike, while that sequence is running,
Yeah.
You know, we've had conversations about various, test signals. Certainly, you're displaying the log chirp signal, but using with the system especially for Bluetooth, either speech signals, other broadband signals like music, noise-based signals. Is that
Absolutely appropriate, especially for the hands-free phone link. You can very easily use broadband noise or speech, and in fact, our analyzer software comes with speech files so that you can just use them as output files. So you don't even have to create it or go looking for it. It's built into the software. I very briefly mentioned transfer function, and it's another efficient way of getting response data, and it actually does exactly what it says. It produces a transfer function plot. But for something like an amplifier channel, it's going to show you much the same as a frequency response plot. It's going to give you that information. The nice thing about it is that it can, for example, do things like plot the sensitivity of a measurement mic against that of a PDM mic, a digital mic, and let you see the transfer function. Or I should say that differently. I was mixing two different things I was thinking about. It lets you see what the analog element was that was transmitting the signal and the digital signal that was received, so that you actually get analog versus digital transfer function data, and that's pretty cool thing. I was thinking back to other tests I've done that used that function for microphones, and it was probably not appropriate. So here is this report. Just quickly scroll through it. Lots of data, lots of date and timestamp information, all the plots that were produced, and this just collects every single result that was left checked on in the system. There's that transfer function. So yeah, and you can see it's magnitude dB, volts RMS versus full scale digital. So So that, I think, covers the bulk of what I'd hoped to cover here with this presentation. I hope you found it useful. Something there seemed interesting.
This is a good point to wrap things up. On behalf of both Mike and myself, thank you for joining us. Enjoy the rest of your day, and thank you for your participation.
Thanks a lot, folks.
Find out more at Vicom's website.